Let us finish section 6.3. We have one thing left. So let me go back to this handout. In this handout, we discussed how to prove set identities. However, what we have not discussed yet is the following. What if we want to disprove something? For example, please take a look at this. Over here. A minus B union B minus C is equal to A minus C. Let us try to disprove. We have to come up with a control example. Step one, we draw a Venn diagram. This is A, this is B, this is C. Next step, let us put numbers inside each region. Here's what I mean by that. Region number one, let me zoom in. Region number one, number two, number 3, 4, 5, 6, 7, and we denote the whole thing by 8. Next, let us consider the following sets. A, which consists of 1, 2, 4, 5. According to this picture, indeed, this set A consists of 1, 2, 4, 5. Similarly, B consists of the following numbers: 2, 3, 5, 6. It's exactly what we see here: 2, 3, 5, 6. Lastly, set C consists of the following numbers: 4, 5, 6, 7. It's exactly what we have here: 4, 5, 6, 7. Now let us go back to our identity. The left-hand side is A minus B union B minus C. So let us find A minus B first. A is this, B is this. Therefore, A minus B consists of just two numbers, 1, 4. Similarly, B minus C is 2, 3, and A minus C is 1, 2. Now, the left-hand side is A minus B union B minus C, which is 1, 4 union 2, 3, which is 1, 2, 3, 4. Note that A minus B union B minus C is not equal to A minus C, which gives us a control example. We are done. Any questions here?
Is there a situation where a Venn diagram drawing might not be the most convenient way to solve the problem?
Well, in this course, the best way to come up with a control example is to draw Venn diagrams. Moreover, please take a look how we draw Venn diagrams. We wish to make sure that all three sets have common elements. We don't draw, for example, C somewhere separately. AB have common elements, BC have common elements, AC have common elements, and ABC have common elements. This gives us as many degrees of freedom as we need in order to come up with a control example.
Yes.
Does this answer your question?
Yeah, that makes sense.
Mm-hmm. By the way, we can use this method in order to check if our identity is true. We draw a Venn diagram, we put numbers. If everything is fine, then try to prove it. If you see that we get a contradiction, here's a control example. Okay, next. Section 6.4. In 6.4, we discuss the following. Let us compare two tables. Let us first go back to section 2.1 and take a look at this table. And then let us go back to set identities. Section 6.2, this one. So please take a look. We have some similarities between logical equivalences and set identities. In both cases, we have commutative laws. In both cases, we have associative laws. In both cases, we have distributive laws. Then, please take a look. In both cases, we have identity laws. But now be careful. Going back to logical equivalences, identical laws are, if we consider P and tautology, we get P. If we start with P or contradiction, we get P again. In set identities, if we consider A union the empty set, we get A. If we start with A intersection the universal set, we get A. So it looks like if you compare this and this, a logical AND plays a role of intersection, tautology plays a role of the universal set. Now let us compare this and for A. It looks like union plays a role of a logical OR, and the empty set plays a role of contradiction. Please take a look at negation laws. P or negation of P is equivalent to tautology. Compare with 5A. A union, A complement is equal to the universal set. So it looks like complement plays a role of negation of P. Number 6, double negation law. Here, double complement law. Number 7, A union A is A intersection A is A. Over here, P and P is equivalent to P, P or P is equivalent to P. Compare also 11 for logical identities and 11 for set identities. Complement of the universal set is the empty set over here. negation of tautology is equivalent to contradiction. Here, complement of the empty set is the universal set. Over here, negation of contradiction is equivalent to tautology. So therefore, next question is, why do we have these similarities? Is this a coincidence or there is some rationale? It's exactly what we discuss here. Let us talk about so-called Boolean algebras. So once again, over here, we show similarities between logical equivalences and set properties. And here we compare these tables again. So let us read carefully what is written over here. If you let OR correspond to union and correspond to intersection, tautology correspond to the universal set, and contradiction correspond to the empty set, negation correspond to complement, then you can see that the structure of the set of statement forms with operations or and is essentially identical to the structure of the set of subsets of a universal set with operations union and intersection. In fact, both are special cases of the same general structure known as a Boolean algebra. Here is what we mean by Boolean algebra. Please take a look at this. A Boolean algebra is a set B together with two operations denoted by plus and times, such that for all A and B in B, both A plus B and A times B are defined and the following properties hold. Number one, commutative laws. Number two, associative laws. Number three, distributive laws, identity laws, complement laws. So here we have 5 laws. Let me ask you a question. If we compare plus here and logical operations, what do you think? Plus is or and?
Is plus or?
Plus or times
And?
times and. If you compare plus and times with set operations, plus is union or intersection?
It makes sense that plus would be union, but I don't see how multiplication would be intersection.
So question is, how come that multiplication is intersection? What's the problem?
I guess the way we're taught multiplication is that it's kind of like adding several times.
No. Look, David, it's a very good point. So forget words addition and multiplication. Call plus operation number 1. Call times operation number 2. Now let me restate my question. What do you think? Operation number 1, talking about set identities, is it union or intersection?
It's union in set.
Union. Operation number 2, is it union or intersection?
Intersection.
intersection. May I ask a question? This symbol, 0 in sets, means what?
Null?
Null set. How about this symbol, 1, in sets?
An existing set?
Universal set.
Yes.
So now think about identity loss. A plus 0 is equal to A. In sets means the following. A, set A, union. The empty set is equal to set A.
Yes.
Talking about 4B. Can you translate 4B into the language of sets?
The intersection of A and the universal set is A?
The intersection of A and the universal set is A.
It's making sense now. I see it.
You see it now?
Yes, I see it now.
Talking about logical operations. Can you translate this and this into the language of logic?
A or contradiction is A.
A or contradiction is A. Let us go back to this. P or contradiction is P, correct?
Yes.
How about this?
Then that would be A and tautology is equal to A.
P and tautology is equivalent to P, correct?
Yes.
It's exactly what is written here. P and tautology is equivalent to P. How about this? In sets, 4 sets. Can you translate this into the language of sets?
And A bar is the complement or negation.
Say it again.
I was looking for the definition of A bar. So that would mean in set notation, that's the union of A and A complement is the universal sets, right?
Exactly. Talking about sets, A bar means complement. Talking about logic, A bar means what?
Oh, in logic, A bar is a negation of A?
Negation, absolutely. So going back to sets, 5A means what?
What A means what?
5A for sets
The
means
sets.
what?
Just the set A in B?
So left-hand side is what? A union.
Oh, A union A complements.
A complement is equal to
The universal set.
the universal set. 5B.
The intersection of A and A complement is the null set.
The intersection of A and A complement is the null set. It's exactly what we see here. Number 5. A union A complement is universal. A intersection A complement is the empty set. Now,
Yes.
talking about logic, 5A means what?
In logic, that would mean A or A negation is equal to true.
So let us be a little bit more precise. P or negation of P is equivalent
It's equivalent to tautology.
to tautology. Talking about 5B,
That would be P and negation P is equivalent to contradiction.
P and negation P is equivalent to contradiction. It's exactly what we have here, negation loss. So once again, 5 here is equivalent to 5 here. P or negation of P is equivalent to tautology. P and negation of P is equivalent to contradiction. Guys, any questions here?
Can you give an example of what, if pick A being a number, what a complement would be? I'm just trying to visualize how A plus A complement is equal to 1, and what does 1 mean in this case?
So depending on a situation, 0 and 1 and bar mean different things. For example, talking about sets, by 1 we mean a universal set. By 0 we mean the empty set.
Oh, okay.
By bar we mean complement. So this is not really 1. This is not really 0.
Right, okay.
Apply these rules in our context.
Okay, I understand.
To either logic or sets.
So little a and little b are both examples of sets. Is that what you're saying?
Yes.
Okay, so, gotcha.
Applying these rules to sets, A, B, C are sets.
Okay.
If we want to apply these rules to logic, A, B, C will be statement variables. Does this make sense?
I guess so, but why are you doing it in terms of Boolean algebra? Like, what's the reasoning for doing Boolean algebra then in this case?
The reason is the following. We see similarities between logical equivalences and set identities. We're trying to explain why logical equivalences look like set identities.
Okay, so what do they call 1, 0 in Boolean algebra? Is that just they wouldn't call it?
Yeah, we call it so in Boolean algebra they call it 0 and 1.
Oh, I guess, okay.
But this is how we call it. You can call this operation plus, you can call this operation times, you can call it. But in particular, plus in Boolean algebra means union in sets. Times in Boolean algebra means intersection in sets.
Okay, and then 1 and 0 is that the same as true and false, or
No.
just unit like
0 in logic means contradiction. 1 in logic means tautology.
Okay, I see, I understand.
0 in sets means the empty set. 1 in sets means the universal set.
Okay.
Does this answer your question?
Yeah, I got it, thanks.
Now, you may ask me a question. Wait a second. Here we have just 5 rules. And these 5 rules correspond to these 5 rules. How about double complement law, universal bound law, De Morgan's law? The answer is we can deduce all these laws from these 5 rules. For example, please take a look at this theorem. Uniqueness of the complement law, uniqueness of 0 and 1, double complement law. By the way, double complement law corresponds to double complement law for sets and double negation law in logic. So, in other words, we will use only 5 rules from this definition in order to deduce the rest. And here we have, in this theorem, we have 8 additional laws. And then the remaining laws in sets and logic will follow from this. For example, De Morgan's law. A plus B bar is A bar times B bar. AB bar is A bar plus B bar. In the language of logic, 6A corresponds to 9B, and 6B corresponds to 9A. If you compare this with set identities, 6A corresponds to 9A and 6B corresponds to 9B. Think about questions. So once again, what we see in front of us here is definition. We have 5 basic properties. And then from these 5 basic properties, we deduce the remaining 8. And then the remaining property here and here follow from these 8 properties. Last thing for today are Russell's paradox. Let us consider the following set S. The set S consists of all sets that are not elements of itself. Question: is set S an element of itself? Unfortunately, we cannot really answer this question. The answer is neither yes nor no. And this is why we call it paradox. Here's why. Well, there are 2 possibilities. S is an element of itself, or S is not an element of itself. Suppose S is an element of itself. If S is an element of itself, then S does not satisfy this property. Since S does not satisfy this property, S cannot be an element of itself. Therefore, S is not an element of itself, and we get a contradiction. If S is an element of itself, S is not an element of itself. Vice versa. Suppose S is not an element of itself. If S is not an element of itself, then S does satisfy this property. Means S is an element of itself. So if S is not an element of itself, S is an element of itself, and we got a contradiction. Any questions here?
Can you explain this once again?
Yes. So set S consists of all sets that satisfy the following property. A is not an element of itself. Now, for set S, there are 2 possibilities. S by itself is an element of itself, or S by itself is not an element of itself. Now, in both cases, we get a contradiction. So, case 1, suppose S is an element of itself. Since S is an element of itself, it does not satisfy this property, correct?
Yes.
Because S is an element of itself. Here we consider the set of all sets that are not elements of itself. So since S is an element of itself, S is not from this set, correct? Therefore, S is not an element of itself because S is not here. Because if S is here, S is not an element of itself, but S is an element of itself. So S cannot be from here. Since S is not from here, S is not element of itself. We got a contradiction. We started with the following: S is an element of itself. We came up with the following contradiction: S is not an element of itself. Does this make sense?
Yes.
Correct?
Mhm.
Now, case 2. Suppose S is not an element of itself. Since S is not an element of itself, it does satisfy this property. Correct?
Yes.
Since S does satisfy this property, S is from here. Since S is from here, S is
Boolean contradiction.
itself, which is exactly what is written here. We got a contradiction. S is not an element of itself, and S is an element of itself. In both cases, we got a contradiction. Does this answer your question?
Yes.
Jimin, yes.
So how do you deal with the fact that the statement is either true or false?
So
the-
exactly, question is how to fix the problem. One way to fix it is to start with a universal set. Remember, a universal set is a set that contains everything in the context of our problem. So in our problem, we deal with sets. Let us assume that all these sets belong to a universal set. In other words, instead of considering this, let us consider this. Suppose S is the set of all sets A, such that A is not an element of itself and A is from some universal set U. We will finish this handout on Wednesday. You will see that if instead of this S, we consider this set S, we will not get a contradiction in both cases. Does this answer your question?
Yeah.
Mhm. Other questions? All right, guys, if you don't have questions, we're done for today. Bye.